So welcome to the next seminar, the last in this semester. Today we are having Karol Węgrzycki about subset sum.
Yes, thank you. So I will talk about joint work with Jesper Nederlof from Utrecht University. I will talk about subset sum algorithm for algorithm. So what is a subset sum? So in the subset sum problem, you are given a set of n integers. In this case, it's 6 integers and a target t, which is 27. And the goal is to find a subset of subsets of this of the numbers in this set, such that all the numbers are summing to this target. So in this case, you can answer yes, because 2 plus 9 plus 16 is equal to 27. And in this talk, we consider the exact algorithm for a subset sum. So first improvement was given over the naive 2 to the n algorithm was given by Schroeppel and Shamir in 1974. And they showed that subset sum can be solved in 2 to the n half time and 2 to the n half space. And the big open question in the area is to give some improvement over their algorithm in the worst case. Yeah, their algorithm is called meet in the middle. So I would say meet in the middle, I am thinking about their algorithm. And then 5 years later, Schroeppel and Shamir improved the space complexity of their algorithm. So Schroeppel and Shamir had 2 to the n half space algorithm, and now we have the 2 to the n quarter space algorithm. And at the end of their paper, they asked whether you can improve the space complexity a bit. And in this talk, we say that yes, you can improve the space complexity to be 2 to the 0.249999n space. And yeah, just a quick remark, you can generalize this algorithm for knapsack and binary integer programming via the known equivalence reductions. Yeah, so that's basically all the results we have. Before I proceed with the description of the algorithm, let me tell how this question, whether you can break meet in the middle for subset sum, influenced different areas of the theoretical computer science. So firstly, it influenced the cryptography. With this question, we have the meet in the middle algorithm, but also we can have the Merkel-Hallman systems. There was a big progress on average case knapsack by Horowitz and Hograf and Zhu in 2010. We also have, thanks to this question, the SVP and LLL. And recently it gave rise to the representation technique in the cryptography. And then in the fine-grained world, this knapsack problem was the original NP-complete problem by Karp. And this question is basically the basis for the K-sum conjecture, and we have something that is called free-sum equivalence and plethora of other lower bounds, such as that you cannot have pseudo-polynomial algorithm that works in t to the 0.99 algorithm for subset sum unless strongly th. So this work inspired a lot of lower bounds in the fine-grained regime. We also have a couple of pseudo-polynomial algorithms that were inspired by this work. The work of Karl Brinkmann that showed that you can solve subset sum in O tilde of t running time. There were a couple of papers on lower bounds for knapsack problem and a couple of lower bounds in the fine-grained regime for the approximation algorithm for knapsack and subset sum. And finally, I want to claim that there was some progress on exact and FPT algorithm for knapsack. So most notably, Banzal et al. Showed that knapsack can be solved exactly in 2 to the 0.86n time and polynomial space. Then Nederlof et al. Showed the equivalence of knapsack and subset sum in the exact FPT. That there was some progress on time-space trade-offs for knapsack by Dinur and some parameterization by Austrian et al. So you can solve this. You can solve subset sum in this 2 to the 0.49999 time when instance has some nice parameter. So now when we know the related work, let me present to you the simple meet-in-the-middle algorithm by Horowitz and Shamir. So recall that in the subset sum you are given the set of n numbers and a target t, and your goal is to find a subset of indices of these numbers such that the total weight of this set is equal to t. All right. So first step of the algorithm is basically to partition the numbers into two groups of size and half, to left and right partition. And then what we do is we basically enumerate all the subsets of this capital L set, and we call it calligraphic L. This set has size 2 to the n half, because this is the number of subsets of set of size n half, and we call it calligraphic L. And we do the same on the right partition, and we enumerate all the subsets of the set capital L, and we call it capital R. So I'm using this notation that the weight of the set family is the set of the weights of all the sets in this family. Okay. And then what we do is we sort this calligraphic L and calligraphic R sets, and we can do a lot of strange things to find the set X in calligraphic L that and set Y in calligraphic R that have sum equal to T. We can, for example, iterate over all sets in all numbers in calligraphic L and do the binary search to look for the set that has some T minus 6 in calligraphic R because it is sorted, or we can do this this clever two-pointer technique to have the pointer on the lowest element in calligraphic L and the highest element in calligraphic L and smallest element in calligraphic R, and depending on whether the sum is equal to T or smaller or greater, move one of the pointers. So for example, now the sum was too low, so we have increased the total sum and we have moved this pointer in this calligraphic R, and now it's too small, so we have decreased the sum. And after linear iterations, we finally arrive and find this set, these two sets that have sum equal to T. And if we have this set, then we answer yes, because obviously this is they give you the set that has sum equal to T. And the running time of this algorithm is 2 to the n half, and the space complexity is bounded by the size of this calligraphic R, so the space complexity is also 2 to the n half. Yes, that's clear. Okay. Let me do something more complicated. So let me present to you 2 to the n quarter space algorithm. So the idea is as follows: we divide this set into four subsets, and we basically do the same. So we enumerate all the subsets, all the weights of the subsets in this in all of these sets. And we sort them, and basically I can just say that we solve for-sum problem on those. So in the for-sum problem, you are given four sets of numbers and a target T, and your goal is to decide whether there is a set of numbers that sums up to T. And let me sketch to you how this for-sum algorithm works. So this for-sum can be solved in n square time and linear space. So the Schroeppel and Shamir idea to do that is to generate on the fly this set calligraphic L that Horowitz and Sani had, and this set will have the some set of calligraphic L1 and calligraphic L2, and it will use only the space complexity of keeping this data structure for calligraphic L is linear in the input. And it has the property that you have the immediate access to the lowest element in this data structure, and you can get in the polynomial time the next lowest element after removing this smallest element from this priority from this data structure. And what Schroeppel and Shamir do is construct the same data structure for this calligraphic R set with the property that on the top you have the highest element in this calligraphic R, and then you merge this solution using this two pointers technique. So you start with the lowest element in this calligraphic L and the highest element in this calligraphic R, and depending on whether the sum is smaller or equal, you remove this smallest element from this calligraphic R or calligraphic L, and you put your pointer on the next element. And after some iterations, after removing or adding elements, you arrive at this two pointers that indicate whether you have that will be the witnesses of your set. And since this for-sum algorithm works in quadratic time and linear space, you can solve subset sum in this claimed time, in the middle time and to the n quarter space. And that's basically what was the best algorithm so far. Any questions about that? Okay, so let me tell you some literature. So Węgrzycki and Zhu showed how to solve subset sum on random instances in this 2 to the 0.337 n time and 2 to the 0.256 n space. And this is not what we want. This is an average case subset sum. We solve it in the worst case. And what they basically showed is they introduced this super nice technique that is called representation technique. Next, it was used by Ostrin, Koivisto, Karski, and Nederlof to solve subset sum faster than within the middle time for large classes of instances. So if I would like to sum up the representation technique on the picture, it would be something like that. You are given a searching problem, you are searching you are having some search space and a solution that you can think about a needle in a haystack, and the goal is to find the needle. So what Węgrzycki and Zhu propose is to increase the size of this haystack, and in such a way that you also increase the number of solutions to your problem, and then somehow sample this solutions and consider only the smaller space. And we'll explain in the middle what is going on. So, but you can think about increasing the search space and then randomly selecting the small portion of the space with a guarantee that the solution with high probability exists. And then what Ostrin et al. Showed is they showed the reduction from subset sum to orthogonal vectors, and they have 3 steps basically. They have meet in the middle, they have representation technique, and they use a naive algorithm for orthogonal vectors. So first, what is our contribution is we replace this naive algorithm for orthogonal vectors with a bit faster algorithm for orthogonal vectors, and we arrive at the 2 to the n½ time and 2 to the 0.499. Actually, there's a lot of nines here. Space algorithm. This is not what I have claimed, but basically this is all I will show you on this talk. Yeah. So what is this crazy orthogonal vectors problem that I keep talking about? So in this orthogonal vectors problems, you are given 2 sets, a calligraphic L and calligraphic B of d-dimensional vectors and the task is to decide whether there is a pair that is orthogonal. So whether this product is 0. You can think about this as a set intersection problem. So you are given two families of the subsets of this universe, and the goal is to find two sets that are disjoint. And the two known algorithms that are trivial for these problems are the quadratic time. So you enumerate all the sets in A and all the sets in B, or you can have an exponential time in the universe size algorithm that is linear. There are slight improvements known, but nothing that is strongly subquadratic in n when d is sufficiently large. And in this talk, we will be considering the algorithms that are linear in size of n, and we will focus on improving the exponential dependence on d for some instances of the orthogonal vectors. Yeah, let me tell you how we improve the algorithm for subset sum. First, we took this reduction from subset sum to orthogonal vectors, and then we have added this faster algorithm for orthogonal vectors that works in this time that matches the meet in the middle. And then the next idea is to basically replace meet in the middle with Schroeppel and Shamir. It is the intuitive next step, but yeah, unfortunately, if you do that, you would have a little worse complexity in the running time. It will still beat the known trade-offs between the time and space complexity, but this is not what we are aiming at. So the second idea that we are having is to find a new, to add some new ideas to representation technique and arrive at this 2 to the n-half time and this 2 to the 0.24999 in space algorithm. Okay, so that's basically the plan of the talk. I hope I will tell you about first, second step, and a little about and sketch how the fifth step is done. Any question about this figure? Okay, so let me tell you some assumptions. They're pretty crucial. So assumption one is that the solution to subset sum in the worst case is half of the elements, right? So basically the argument for this assumption is that because otherwise you can solve subset sum faster. So let's assume that the solution to subset sum is smaller than 2 to the n-half or strictly greater than 2 to the n-half. Then what I want to claim is that Schroeppel and Shamir works perfectly. So what we could do is we could randomly split the instance into 4 parts, and then with high probability, because we assume that our solution is smaller than 2 to the than n-half, the solution intersection of solution with this one partition will have size smaller than n8. And then if we enumerate this n8, this sets calligraphic L1s and calligraphic Ris will have size smaller than 2 to the 0.24999 n. And then we can plug it into the four-sum algorithm, and it will give you the faster running time in space. So this is just the first assumption. And then I will have some second assumption that is not that trivial, but I assume that if you randomly select a subset of n numbers, then you have then this set will generate 2 to the size of this set different sums. Okay, so I can assume that because otherwise Schroeppel and Shamir works fast enough, and the idea is basically the same. So I assume that you have this set calligraphic M, and it generates less than 2 to the m sets. Then I'm claiming that you can select the sizes of this partition in such a way that these sets that are generated by this calligraphic L sets are smaller than 2 to the 0.24999n. And this is basically because this set generates less than 2 to the m sets. And then you plug it into for sum and it also works. Okay. So now I will show you the Austrian et al. Reduction with this assumption. And we will see how representation technique works in this regime. So yeah, the reduction is very it's amazing. So first we have just assumed that we have randomly selected this set capital M that generates a lot of the distinct sets. So we split the rest of the instance into calligraphic L and calligraphic R. We can split it arbitrarily. Okay, and let me present to you the easy algorithm for subset sum. So the algorithm is as follows. We again are going to enumerate all the subsets of this calligraphic of this capital L, but we are going to add the sets from capital M to it, and the same for this calligraphic R set. So this calligraphic R set is just every subset of 2 to the R plus 2 to the M. And then what we would like to do again is to do this binary search procedure, but it doesn't work right away. We need to add this disjointness test because the solutions to this L and in this calligraphic L and in this calligraphic R may have some elements that are intersecting here. So we also need to check whether the sets are disjoint. So if there are disjoint, then we can, if there are disjoint and have sum equal to T, as in here, then the solution to subset sum is found. Okay, this is slightly worse algorithm. It's worse algorithm than what I claim always. So let me improve upon that. I haven't used the assumptions yet. So let me use the assumption 1. And what I'm claiming now is that the extreme case is only when this sets, we only need to enumerate sets of size m quarter. Basically, this S intersected with M is of size m half. So enumerating m quarter, sets of size m quarter is enough. Because if there is a solution, then there is a solution such that the left part in it is of size m quarter, and the right part of solution in M is also of size m quarter. So basically, I can enumerate only the search space is 2 to the L. I'm still enumerating all the subsets of capital M, but I'm enumerating only the subsets of size m quarter. To get this M choose M quarter. And then again, I'm doing this orthogonal vectors, this disjointness test for orthogonal vectors. Yeah, so what we have done so far seems pretty naive. We had the search space of size 2 to the n half, and we have increased it to be 2 to the L plus M choose M over 4. But here, if you recall this figure, that is what we wanted. Basically, this is how representation technique works, and we are going to have some nice observation now. So the observation is to use the assumption 2. And the observation is that basically there is 2 to the M, size of M half, different pairs of numbers, AI in this L plus M and A2 in this L plus M, such that they constitute for a solution. And this is because this set capital M generates a lot of different sums. Okay, so what we had is we had a solution for subset sum, and now we have like 2 to the M half solutions for subset sum. And what we are going to do now is we are going to sample this set, this solution to consider only the haystack of some smaller size. So what we are going to do now is just to randomly sample the set of size number of solutions divided by the number of solutions, which is roughly this capital small p number. And we have the guarantee that in this calligraphic L and calligraphic R set, there is a solution that there's at least one pair that constitutes for a solution. And then again, we are going to do this orthogonal vectors procedure to find the disjoint sets. And nice thing about this is that the space, the size of this calligraphic L set is smaller than this 2 to the n half. So it's 2 to the n half minus some constant times size of capital M. And yeah, that concludes the reduction of the Austrian et al. So let me go again through it because it's hard to grasp when you see it for the first time. So this reduction of Austrian et al. Is just a reduction from subset sum, and if this is a yes instant for subset sum, then we are creating the sets calligraphic L and calligraphic R with the property that their weight is equal to T, and they are disjoint. So to decide whether the subset sum is yes or no using orthogonal vectors, we are going to sort this calligraphic L into groups of vectors of size exactly I, and the same for this calligraphic R, and run these orthogonal vectors subroutine on every group. And if at least one of the calls to orthogonal vectors answers yes, then we can answer yes to the subset sum. And this sets in calligraphic L and calligraphic R have some nice property. So first of all, recall that there are, and that the support of them is the quarter, or this capital M quarter, and the sizes of this calligraphic L and calligraphic R are slightly smaller than 2 to the n half. Yeah. So this is how the reduction of Austrian et al. Looks like. No questions?
I'm a little bit puzzled here. So the reduction actually gives you some benefit in terms of the expected size of the lists L and R. But what do you pay?
You pay that you don't solve. You need to solve this orthogonal vectors.
I see. Okay. Yeah.
Yeah. That's basically it.
Yeah. Thanks.
So recall that we are considering the linear time algorithm for orthogonal vectors. So the time complexity to solve the subset sum will be the size of the orthogonal vector subroutine run on this calligraphic L and calligraphic R sets. And the nice property that the key insight of our work is that you can design the orthogonal vector subroutine in the running time that is linear in the size of the input times 2 to the CD, where C is exactly the constant that matches the downsize of this of the set sizes of calligraphic L and calligraphic R. And if you combine these two, you will get the subset sum algorithm that runs in 2 to the n half time exactly. And in terms of the space complexity, you only need to remember the size of this calligraphic L, calligraphic R, and one call to the orthogonal vectors at a time. So you have some benefit that you have saved space by having the reduction that is many-to-one reduction. Yeah, so the main insight of our work is this orthogonal vectors subroutine and the fact that it magically matches the running time. So let me present to you the orthogonal vectors algorithm that runs in the claimed time. It's pretty cool, and it is based on the work of Fomin et al. Fomin et al. From 2016 that introduced something that is called representative families. It is used in the FPT world, and and we translate it. We translate their framework to the orthogonal vectors. So we call that in the orthogonal vectors you are given two sets, and the task is to find whether there are disjoint. There are two sets that are disjoint, and we have also the assumption that the support is D over 4. So our orthogonal vectors is designed to work under this assumption, and it will work in this time. So first, I will now present to you the algorithm. So first, a simple observation. You are given two sets, X and Y, and you want to certify that they are disjoint. So if there are disjoints, there must exist a set S, capital S, that is disjoint with Y, and it contains all elements of X. And it works the other way around as well. So if such a set S exists and you only know that it contains X and is disjoint with Y, then you know for sure that your sets are disjoint. Okay, we will call this set capital S certificate of disjointness of S and Y. So first thing, let me compute what is the number of certificates of disjoint for fixed X and Y. And we are only considering this set S to be d-half because this is the extreme option. So number of good certificates for disjointness of X and Y is d-half choose d4, basically because you have to select d over 4 elements from X, and you have a freedom to select d over 4 elements, and you are selecting them among the red and blue region, which is of size d-half. So among d-half elements, you are selecting d quarter elements. So number of good certificates of disjointness of X and Y is d-half plus d-quarter. Okay, and now let's see the algorithm. So we are given the set calligraphic A here and calligraphic B here, and you are randomly selecting two to the d-half sets that are completely random of size d-half. Okay, and next you compute the edges. So I will add an edge between the set X and set S if and only if X is contained in S. Okay, so for every set X, I will iterate. I will look what are the sets that are contained in S, and I will add them to my graph. And for every set B, I'm going to add the edge from Y in calligraphic B to SI if and only if the set is disjoint with Y. Okay, and what we need to do at the end is we need to check if there is a set S that is that has a blue and red edge at the same time. If such a set exists, then yes, we can answer that the subset sum is true. Yeah, any questions about that? I will bound the probability of success now. Yeah, so let's bound the probability of success is as well. So assume that the answer to subset sum is yes, then there are some X and Y that are disjoint, and the probability that a random set S is a good witness for them is number of good witnesses over all the sets that you can select, and this is roughly 2 to the minus d over d-half. And recall that we have randomly selected 2 to the d-half sets, and number of repetition is 2 to the d-half. So the algorithm is correct with high probability. Okay, any questions about this algorithm? About the correctness of this algorithm? Okay, I want to claim that the running time of this algorithm is basically number of edges. I don't want to get into details of that, but you can, for example, observe that these sets from the certificates are oblivious to the input, and therefore in some nice preprocessing time you can get a data structure that answers for a given set X. Here it will give you the neighbors neighbors of S. So I want to claim that the bottleneck of the running time is basically the number of edges. Okay, and now I'm going to bound the size of this graph. So observe that for a fixed edge, the number of sets that are containing it is 3D over 4. Choose D over 4. Basically, you are given this set X here, and you have freedom to select it among 3D over 4 different domain, and you need to select it, and you have freedom to select only D4 elements. So therefore, the degree of this fixed set in calligraphic A is the probability that this set is contained by some set S times number of sets S. And it's this number, and magically this number is equal to this number. This is a tautology. So the size of this graph is number of indices. So number of edges is basically number of vertices times the average expected degree. And so this is the size of this graph, and yeah, this is the running time. And there are a lot of technical difficulties, but you can trust me that they can be avoided. Okay, any questions to this algorithm?
I'm not sure if this is the right moment to ask this question, but in a sense, you are doing here like a randomization of color coding, where one side is the blue guys need to contain X, and the red guys need to contain Y. Would it be possible to replace this like sampling randomly enough sets S with some off-the-shelf construction of a universal hash family?
Perhaps we haven't thought about this. I think
Okay.
there was some work on the randomization for Minetol.
Mm-hmm. Yeah, it's a very specific case, and you very much care about the degrees. But okay, never mind. We can talk about it later.
Yeah, we can check that, but this is not a bottleneck of randomization of our algorithm anyway.
Yeah.
Yeah. So far we saw this reduction. I showed you this orthogonal vectors that works by applying this framework of Minetol, and it gives you the 2 to the n half time and 2 to the 0.24999 space with assumption 1 and assumption 2. And I want to point out that breaching these assumptions is a highly technical task. Next, I want to tell you how you can combine Schroeppel and Shamir with representation technique and what are the technical difficulties there. Yeah, so what is our new idea now? And we want to apply the Schroeppel and Shamir now. So instead, recall the reduction of Ostrin et al. We had this calligraphic L, calligraphic M, and calligraphic R sets. Now we are randomly sampling the set capital M, capital ML, and capital MR that are disjoint, and we assume that they have this property that number of these distinct sets is roughly their size. Okay. So we are sampling, we are having this ML and MR, and the rest of the instance are split among this capital L and capital R. Okay. And what we are going to do now is we do the same, basically the same reduction that Austrian et al. Did. So we are going to enumerate the all of the subsets of L and subsets of ML of size L quarter. And since we have 5 distinct sets here, we are having 4 different possibilities. And then we are going to enumerate this calligraphic L1, calligraphic L2, calligraphic R2, calligraphic R1 with this representation technique. And this clever sampling idea of ours will give us the, the property that this expected size of this sets here is smaller than 2 to the 0.249999n. And we are going to use, now we can afford to use naive orthogonal vectors and this and combine it with this priority clue to have this calligraphic L data structure generated on the fly of Schroeppel and Shamir. And we can even afford this calligraphic L1 times calligraphic L2 time amortized time to generate them. But we will store only, we will use this size of this calligraphic L1 space to store them. And then what we do is basically we do the merging step just as before, but when we apply this merging step between the sets, between the green and the red sets, we use this orthogonal vectors idea of Fomin et al. To combine them and check whether they are orthogonal. So we will have this nice. We will give this new representation technique in such a way that this generated on the fly set calligraphic L will have exactly the same size as we had for the case when we used only meet in the middle. And I just want to point out that there's a lot of technical difficulties. First of all, this when you break these assumptions, when you don't have these assumptions that I didn't justify yet, the sizes of these sets, this generated all these sets that are generated by the sets capital M may be different. We have to do something clever about the algorithm in this case. We also do some non-trivial analysis of the size of this calligraphic L. It requires new idea in representation technique and analyzing this orthogonal vectors technique, even orthogonal vectors algorithm, even when you have when you break this first assumption, is untrivial in order to lower bound the size of this graph when you don't have this assumption one in such a way that you still arrive at the meet in the middle time. Yeah, took us some writing. Let me point out some other ideas now how you can break meet in the middle. So think about this exact not weighted before algorithm. So in this algorithm, we are given a not weighted undirected graph G. So the weights are on the nodes. And the task is to decide if there is a simple path on 4 vertices with weight equal to exactly t. And yeah, so what we show in this paper is that basically that if you would be able to solve this problem fast enough, for example, if you solve it in 2 to the n to the n squared time, then you would break meet in the middle. So the reduction is pretty straightforward when you have all the proofs from the previous case. So we are taking this set between L and capital ML, and we know that it will have only like to the 0.24999 elements, and all of them has some weights. And we do this for every set out of this four set. and we will put the edge between the vertices if and only if they are disjoint. We can afford the naive of it to decide that because we afford the quadratic time algorithm. So now what I'm claiming is that if you would be able to solve it in quadratic time, then you would break it in the middle because this calligraphic n is smaller than 2 to the n quarter. And basically, you can think about our reduction as the reduction to this exact not weighted before. Unfortunately, the naive algorithm for exact not weighted before runs in cubic time, and unless Boolean matrix multiplication to be improved, you cannot hope to get into the omega time. And the best algorithm we know is by Karol, who gave the algorithm that runs into the 2.69 time with the bound. And it would be nice if someone could prove some lower bound on this exact not weighted before algorithm or break Brinkman's algorithm. If you could get an omega time algorithm, it would be amazing. It would mean that you can solve subset sum. You can break in the middle for subset sum when omega is equal to 2. So to conclude, we saw that you can have 2 to the n half time and 2 to the 0.249999 space algorithm for subset sum that transfers to the offset and binary integer encoding programming. And the key insight is that you can use the orthogonal vectors algorithm that matches exactly the middle for subset sum. And in the paper you will also, I want to advertise that you can see how we extended this representation method and some lower bounds on this graph of this orthogonal vectors algorithm. So we basically prove some lower bounds in the size of this graph that you saw. And there are a lot of open questions. So first of all, we have the proof that you can get 249936N algorithm, but it is too complicated and we decided not to write it down. And the big open question, the next barrier that we think is nice is to break it even below 2 to the 0.242n. So this arises when you have all these assumptions, even in your hand, our algorithm cannot break even below that. And the next question is, can you give some ideas to randomize this representation technique? So that's it. Thank you.
Yeah, thanks a lot for the talk. Should we on 3, 2, 1 unmute ourselves and clap? Yeah, so 3, 2, 1. Yeah. Can you just say, before we go to the questions, what happens with the paper in the sense like where was it published and so on?
It wasn't published yet.
It wasn't published yet, but it's on archive?
Yes.
Okay, good. Good. So are there any questions in the room? Okay, it seems that everything was clear. Yeah, so if there are no further questions, then yeah, thanks a lot, Karol, for this talk, and thank you very much for the seminar.